Welcome to Plutus IAS, and today we are covering Werner theory of coordination compound. Now, we all know the coordination chemistry as the Werner's theory as the very first theory that was the first attempt to explain how the bonding in the coordination complexes occur. Now, Werner gave this theory in the year around 1837. Now, for about next 100 years, about till 1918, there was no explanation regarding the bonding nature in case of coordination complex. Hence, the studies regarding coordination complexes were very much limited. In 1918, he was given Nobel Prize for this, and is also called as the father of the coordination chemistry. In 1918, we got the theories like VBT, which we which initially were used to explain the nature of bonding and hybridization and whatever the results that were given by Werner. Now, what separates every other theory from Werner theory is that it was not just was the very first attempt to explain the bonding nature in case of coordination compounds, but it was also experimentally verifiable, that whatever Werner said was can be explained on the basis of experiment, but still, even after all that, he could not explain the actual nature of bonding. But he established the very first concept of coordination chemistry, that happened something regarding the coordinate bond does exist in solutions. So for that, first he gave what is known as postulates. So Werner stated that in a complex, there is a metal center. In the metal center possess two types of valencies. One is called as the primary valency, other is called as the secondary valencies. The primary valencies are the ionizable valencies, that means they are ionic in nature and mostly equals to the oxidation number of the metal center. Now, the concept of primary valency is applicable to both simple salts, because everything in the nature can exist in oxidized or reduced form, as well as in case of complex. But it is the secondary valency which is more significant to us to explain the coordination chemistry. This secondary valency is non-ionizable. Non-ionizable, that means this is not formed by ionic bonding but is rather covalent in nature. And this secondary valency equals to the coordination number of the complex. Now, this secondary valency is also responsible for a definite geometry, definite geometry of the complex, or how the ligands are arranging themselves around the metal center. Now, how did he figure it out? First, so initially, Werner was doing an experiment regarding a cobalt chloride salt in ammonia solvent. Now, he was taking this salt and making it react with excess solution of silver nitrate. Now, for this case, he got multiple different results. For example, if AgNO3 is reacting, it should precipitate AgCl to get you, it should react to give you AgCl with as a white PPT. So, for the first case, if all the chlorides are ionizable in nature, in that case, we get 3 moles of AgCl. Now, that means in this case, the primary valency of cobalt was 3 plus as per the value of the coordination sphere, while the secondary valency was 6. Even if I substitute a ligand inside and keep everything just like as always, keeping NH3 outside, still NH3 The primary valency is still not changing. It still be equals to 3 and coordination number remains to 6, but the formula is changed, and in this case I'll get 2 moles of AgCl. Then if only one Cl is outside, I'll get 1 mole of AgCl, and if all the Cl are part of the coordination complex or are bound by secondary valencies, in such a scenario, I get 0 moles of AgCl, but the primary and secondary valencies are remaining the same. So, with this experiment result, Werner concluded that in case of cobalt and other d block elements, these metal center are bound by two different types of valencies. One type of valency is ionizable, which is giving result with the case of AgCl, while there is another valency of the metal complex that is not allowing to take, which is not allowing this chloride ions to take part into the reaction. So how can we prove that this is actually happening? So there are evidences in favor of Werner theory. Werner theory. Number one, we can check conductance of the solution. Since conductance is defined by the number of ions present in the solution, the more number of chloride ions present as an ionizable species, that means more will be the conductance of that particular complex. So for this case, hole 3, hole 6, this has zero conductivity. This has some conductivity. Higher conductivity, and the highest conductivity is achieved when all the Cl are present as the chloride ion form, and they produce the largest number of ions in the solution, which is equals to 4. Hence they will have higher ionic conductance in the solution. Another case we can follow for the case study of colligative properties. Colligative properties. When these salts are isolated, we can check all the properties, colligative properties like depression in freezing point, etc. Types of properties of this solution. Since colligative properties depends on number of particles produced by a species. The more ionizable a species, that means more will be the number of ions that are being produced in the solution, and higher will be the value of the colligative property that we are getting as per Ventov factor. So hence we can see that Werner theory can also be related with the colligative property to determine the formula of a compound, number of ionizable species that are present in a complex, and hence these can be interrelated. So these are some of the results that favors whatever theory was proposed by Werner. But again the case is, he cannot define the hybridization, how the metal and the ligands are interacting with one another to form bonds. So for such cases, Werner could not define these kinds of things, because at that time the evidence regarding the bonding was very much limited. So it took about 100 years to actually came up with a theory which was VBT, to explain the nature of the coordination compounds. So I hope you have learned something new today. In case of any doubts, you can add it to the comment section and we'll get back to you. And thank you for joining us.